about the de Broglie relationship. Imagine that you have a particle that is moving with a momentum p, then there is a wave associated with the particle. And that wave is actually drawn here. This I say is a particle with a very definite momentum, which means that I know definitely what the wavelength is because I know that it obeys the de Broglie relationship. So I know that lambda is equal to h by p. And because I know the momentum precisely, I know the wavelength of the wave precisely. Now, suppose you ask me where is the particle? Well, suppose you had an experiment that is trying to determine the position of the particle, where will you find it? Well, you see, if you look at this wave, it has some value here, it has exactly the same kind of value there, same value here, same value there, and so on. So therefore, these positions are equally probable because the probability is proportional to the square of the wave. So therefore, when you make a measurement, maybe you will find the particle here, or maybe you will find it here with equal likelihood, and therefore there is a very large uncertainty in the position of the particle. So what is the idea? The idea is that if you have a wave of a definite wavelength, then the momentum of the particle is very certain. You know what definitely the momentum is. But then you do not know anything about the position because the position can be here, there, and it can be anywhere in space. So the position becomes uncertain. So this is a situation where uncertainty in momentum is 0. But uncertainty in position is very large. We will say it is infinitely large. Now, I don't particularly like this situation because I want the particle position to be definite. Maybe I would like it to be located within a region, something like that. Within this region, if I say the wave is non-zero, then I know that the particle is likely to be found in that region, and that is the kind of situation that I would like to have. So how can I arrange that is the next question. Well, for that, I will think of one more wave. So if you look at this red wave, you see that has a definite wavelength. Similarly, if you look at the green wave also has a definite wavelength, but the wavelength of the green wave is different from the wavelength of the red wave. The two waves have slightly different wavelengths. Now, both of these waves, I am not completely happy because you see, if I know the wavelength precisely, then of course I do not know the position at all. The type X, the uncertainty in position is very large. But now suppose I add together these two waves. What will happen if you added together the two waves? You see, for example, at this location, the green wave has a downward displacement, the red wave also has a downward displacement. So when you add the two, the resultant wave would have a large downward displacement. Similarly, here again, the resultant wave would have a large upward displacement. Okay. So therefore, if you think of adding together the red wave with the green wave, what is the result? The result is what I have drawn with the green, the blue color. You see that the result is actually a wave which has been concentrated in some regions. You see its value is large in this region, while in this region the value is small. So by adding together two waves of slightly different wavelength, it is possible to make the uncertainty in position smaller. You can see that the uncertainty in position may be something like this. Actually, one should discuss this in much more detail, but we do not have the time. So by just adding together two waves, you have caused the wave to be concentrated in some region and having lower values at other regions. So if you want, you can think of adding together a large number of waves. This is a mathematical construct that you can do, and this is known as Fourier analysis. And what the result, it can achieve a result where the wave is something like that. Such a wave, you can say, is obtained by as a linear combination of a large number of waves, all having different wavelengths. And therefore, what has happened, you obtained a wave which is localized, and if we say this is the length L, and for such a particle, if you measure the position, the uncertainty in position delta x will be of the order of L. But you had to pay a price for that. The price was actually that you had to superpose waves of different wavelength. And therefore, if you ask me what is the wavelength, then what I would say is you have made the wavelength uncertain. That is how you made the position certain. So there is an uncertainty in the wavelength, but of course wavelength and momentum are related. So if there is an uncertainty in wavelength, there will be an uncertainty in momentum, and you will realize that the more and more uncertain the wavelength is, the more and more uncertain and the uncertainty in position is. So uncertainty in momentum is. So therefore you realize that you see when you try to reduce delta x, what will happen? The uncertainty in position increases. So there is a kind of inverse relationship between delta x and delta p, and this was put on a solid basis by de Broglie, who could actually derive this relationship. The relationship that he could derive was delta x into delta p must be greater than or equal to h by 4p, and this is known as the Heisenberg's uncertainty principle. Okay, we will not worry about this slide. Now, that is only one aspect of the fact that there are waves associated with particles, but another important aspect of waves is that you see, waves can be reflected. Imagine you have a wave that is incident from the right-hand side to the left-hand side. This is a wave pulse, so-called wave pulse, which you can produce. Let us say this is a stretched string that I have here. I stand here and take hold of this end, and then very quickly move my hand up and down, and let us say I can produce this. It is not easy to produce such a displacement, but suppose I can do that. Then what will happen is that the displacement that I produced, you will find it moves along the string and hits the wall. So this is a tight rope, let us say. So I have produced a displacement in a tight rope, which is a wave pulse. Okay. So a wave pulse I have produced on a very tight string, stretched string, and this wave pulse will move, let us say, it will hit the wall and it will be reflected. So let us see that reflection as an animation. So what is the idea? Whenever you have waves, you see when they hit a boundary, an obstacle, what will happen? They will be reflected. So suppose I have two such boundaries, not just one, which essentially means that I have a stretched string confined within two walls. There is a stretched string. Here is a stretched string. And imagine that I produce a displacement as like the one that you are seeing in this animation. So that is the initial displacement of my string. And then what will happen? You will find that this displacement moves, it hits the boundary, then it is reflected there. It will come back and it will be reflected from the other side. And this goes on continuing. So whenever you have confined a wave, notice what you are doing, you are confining. You have the possibility of waves which are moving around. You see, this wave that I have is moving around, because you can see lateral movement of the wave. So that is possible, but in addition to this, actually, it is possible for you to create what are known as some standing wave patterns. And you are going to see them in the next slide. What actually happens is that, you see, if I have a disturbance, that disturbance will move and it will be getting reflected from the boundaries. Now, the initial disturbance that I produce is produced in such a fashion that the reflections reinforce the original disturbance. And therefore, you have the formation of what is referred to as a standing wave pattern that you will see in the next slide. So here is my string, and I have initially produced a displacement which is like that. And if I release it, what is going to happen? You will see what will happen. The whole string actually vibrates. It simply goes up and down. And if you look at this, you will see that there is no lateral movement. There is only sideways, I mean upward and downward movement. There is no lateral movement. Whereas in the previous case, you see, there was lateral movement, and therefore those situations, I will say, they are time-dependent waves. And these ones actually, they are special, and I shall be referring to them as standing wave patterns. So this is a standing wave pattern. Why do you have them? That there you have them because you have reflections from the boundaries. Okay. Essentially, you have confined a wave to a finite region of space, and you have reflections from the boundaries. And if the conditions are right, the original wave and the reflected wave will reinforce one another, and you will have the formation of standing wave patterns. And that is what is happening in this case. Now, this is not the only standing wave pattern that you can set up. You can set up other standing wave patterns. For example, the next possible standing wave pattern is this one. So you see the difference between this and the previous one. In this case, you see somewhere here, there is no displacement of the string in the upward or downward direction. In fact, the displacement is 0. On the left-hand side, if the string is going down, on the right-hand side, the string is going up, and vice versa. So therefore, this is the next possible simplest standing wave pattern. In comparison with this, you see the previous pattern. There was no point where there was no displacement. Sorry, there was no place where the displacement was equal to 0 in this string, except of course at the boundaries. And at the boundaries, you have fixed the string, therefore it cannot move. So this situation where you have no displacement right at the middle of the string, this we shall refer to as a node. And in fact, in this case, the node is a point. And if you ask a mathematician, he will tell you that a point is zero dimensional. Okay, and the string itself, if you think of the string, again, ask a mathematician how is a string dimensionally, the answer is that it is one dimensional. So the thing that I want to tell you is that if you have waves in one dimension, then you can have points where the value of the wave is 0, and these are referred to as nodes, and nodes are 0 dimensional. Okay, you can think of more complex standing wave patterns. Let us see another one in the next slide. So here you see that there are 2 points, one here and the other one there, where again the displacement is 0. And so there are 2 nodes. And again, nodes are 0-dimensional objects in this case because your wave is in 1 dimension. You can easily think of a more complex. You see, for example, this is, sorry, let me just go back. So here is a situation where you have 3 nodes, then you can think of more complex situations. I mean, all the standing wave patterns are shown together. And so you can ask how many such standing wave patterns can you think of? The answer is, see, it depends upon the number of nodes. You can have number of nodes. If I denote it as n, you can have n equal to 0, n is equal to 1, n is equal to 2, 3, 4, etc. You can think of any integer. So therefore, how many such standing wave patterns you see? As many integers as you have, and of course that is infinite. So therefore, one says that you have infinite number of standing wave patterns possible, right? But of course, the simplest possible one, this is the simplest possible one. It has no nodes. This is the next possible one. It has one node. The next possible one has 2 nodes. The next one has 3 nodes, and so on. So as you go up, you see the number of nodes goes on increasing. And you can think of an infinite number of such standing wave patterns. Now you think of waves in a rectangular membrane. Imagine I have a stretched membrane which is rectangular in shape. And imagine that I take my hand and hit it here. At that location, I would have produced a depression which looks like this. And what will happen? That depression that I have produced will, as time passes, it will move around. It will move around. Maybe it will come here. It will get reflected and go and so on. Therefore, you have what is referred to as a time-dependent wave, and that is what you are going to see. Okay, you have produced an initial depression here, and it is moving. It is reaching here, and then it is getting reflected back. So this is actually a really time-dependent situation where the waves, shape and size, everything is changing as a function of time. So this is a very clear example of a disturbance that is time-dependent. And further, you see, it is confined to the rectangular region. Why? Because that is because your membrane is fixed along the peripheries of this rectangular region. It is actually like a rectangular drum. If you have ever bothered to make a rectangular drum, this is how it would be. Now, of course, you see, you can have standing wave patterns like in the case of a string. So the simplest standing wave pattern that you can imagine is this one, where you can see that the whole of the membrane is in the middle, it goes up and down. So the membrane is simply going up and down, it is vibrating. So this is the simplest possible standing wave pattern, and this has, you see, there is no displacement at the boundaries. There is no displacement at the boundaries. Why? Because that along the boundaries, the membrane is fixed. And right at the middle, there is an upward or a downward displacement. And so this is the simplest possible standing wave pattern. Let us look at the next possible standing wave pattern. This is the next possible one. And if you look at this, you will realize that you see along this line, there is no displacement of the membrane. On the left-hand side, if the membrane is going up, then on the right-hand side, at that instant, the membrane will be going down, and vice versa. And along this line, there is no displacement, so this is a node. You see here, we are thinking of waves in 2 dimensions because the wave is on a membrane. And then what do you find? You have a node. What is the dimension of the node? Node is actually along a line. And so the dimension of a straight line is actually 1. So if you have waves in 2 dimensions, the nodes are 1-dimensional. Now you can think of the next possible standing wave pattern. This is similar. And you have, well, I have to draw this carefully. You have a node along this line. I hope that is visible. Well, I have not been able to draw it properly. I think it is the next one. Right along that line, there is a node. This node is actually different from the previous one, because if you remember what how the node was in the previous case, this node is perpendicular to the previous one. So that is why the two standing wave patterns are different. Can also think of more complex standing wave patterns. This one, for example, you will see that there are two nodes. One is along this and the other one is along that. Okay. So therefore here there are two nodes. And this is a nice standing wave pattern. You can think of more complex ones. I think I have one more. Now you can actually count the number of nodes. In this case, you have 1, 2, 3 in one direction and 1 in the other direction. So in total, there are 4 nodes. Okay. Now you can go on thinking of standing wave patterns having larger number of nodes. But the important thing is, you see, if you think of the simplest standing wave pattern, it has no nodes. The next one has one node, the next has 2, 3, 4, etc. So how many such standing wave patterns? The answer is an infinite number of standing wave patterns can be imagined. And they are different in that their number of nodes is different, or the way the nodes are is different. So this is the case of a rectangular membrane, but of course you people know that rectangular drums are not common at all. In fact, I have never seen one. These are the different possible standing wave patterns. We have really already discussed them, so let me not spend time. What we have usually are circular drums, and if you had a circular drum, the different possible standing wave patterns. Here also it is possible for you to think of traveling waves whose shape go on changing. But for us at the moment, more interesting are the standing wave patterns. This is the simplest possible standing wave pattern. It has no nodes. This is the next possible standing wave pattern. It has one node. If you think about it carefully, you will see that this one node is actually along a circle. Again, I have to be a little bit careful in drawing it, something like that. If you observe carefully, you will see that that is a node because there is no displacement along that line, that circle. I'm sorry. Then the next possible standing wave pattern is this one. It has two circular nodes. This is another interesting pattern. It has one node. Where is that? It is along a line, one straight line, something like that. Along that line, the displacement is 0. And if you think of this one, along such a line, again the displacement is 0. And in this case, a little bit difficult to locate, maybe something like that. And something like that. These are the two lines along which the displacement is 0. So therefore, this one has two nodes. This has one. This has one. This has two nodes. This one has one node. The nodes are circular in these two cases. In this and in that, the nodes are circular. In the other cases, they are straight lines. So how many such standing wave patterns can you imagine? The answer is just as before. Infinite number of such standing wave patterns can be imagined. And the simplest one is here. It has no nodes. So that is something that you need to remember. Now, what is the connection of all this with chemistry or physics or nanoscience? Well, let us think of an electron, a very tiny particle. It doesn't have to be an electron. You can think of an atom like helium atom. And imagine that you have confined it inside a box. For sake of illustration, I will say that the box is two-dimensional, but that is not necessary. You can think of three-dimensional boxes. When I say two dimensions, you see, for the physicists, two-dimensional box is actually a three-dimensional box, except that its thickness thickness of the box is very, very small, which means that two dimensions of the membrane of the box are large, while the other one is very, very small. So imagine you have an electron put inside such a box, two-dimensional box. So therefore, effectively, it is moving only in two dimensions, because in the third dimension, the dimension of the box is very small, and there is a boundary here. You may say this is artificial, but you please wait. Then imagine you have an electron. This electron is definitely a particle, so therefore you can imagine it is moving, going to move in this direction. And when it is moving, you see, what will do is it will encounter that boundary. It will encounter this boundary. And when it encounters the boundary, you can say it is a wall. Therefore, what will happen? The particle is going to get reflected. So the particle after reflection will move in this direction. But then this is not really a classical particle, but it is a quantum mechanical particle, because it is an electron. It has a wave associated with it. So if you say the electron is getting reflected, that actually means that the wave associated with the electron, which is shown here, this wave, too will get reflected. So the wave is getting reflected. So therefore, essentially, when you have confined the electron to within this box, you are confining the wave associated with the electron to within that box. And once that wave is confined, as we have seen just now, this wave can form definitely a time-dependent wave pattern, where the shape goes on changing. So it is possible for the electron the electron wave to be moving around, changing the shape. That is definitely possible. But there are also special case situations where the wave associated with the electron will form a standing wave pattern. So therefore, it is possible for the wave to be inside the box to be having a standing wave nature. And how many such standing wave patterns can you imagine? We already know the answer, an infinite number. And what about the simplest possible standing wave pattern? That will not have any nodes. The next one would have one node, the next would have two nodes, and so on. So you may say that, okay, this is a rather artificial example, but it is not, as will be demonstrated in the next slide. So here is a very interesting experiment done around, I think, around 1998 or so. Or it could be earlier, maybe 1988. This was done by, the experiment was done by Eigler in the IBM Zurich laboratory. So what he did was, he had a copper surface, metallic copper, the surface, he took the surface. He took that particular surface because he knew that there were electrons which were essentially confined to within a few angstroms of the surface. You see, they were not allowed to go into the bulk. That was the nature of the surface. Not all electrons, some electrons were confined to the surface, which means that, you see, if this is the surface, they are confined to the region of thickness, something like 5 or 10 angstroms within the surface. So on that surface, and here you are seeing the top view of the surface. This is the top view of the surface. And what he did was, he arranged iron atoms. So these peaks that you see in the figure are actually, each one of them is an iron atom. He had built a special scanning tunneling microscope using which he could manipulate atoms sitting on a surface and arrange them on the surface, and that is what he did. These were all Fe atoms, iron atoms. And these iron atoms were arranged in the form of a rectangular box. And I have already told you, within this region, there are electrons around the surface. And the idea was that you confine these electrons to this box. Why? How? Well, these iron atoms will prevent these electrons from moving out easily, and therefore these electrons are confined. So then what will happen? These electrons which are within that region, they have waves associated with them. So these waves can form standing wave patterns within the box. So therefore, what you will find, there are waves within the box which are standing waves, and correspondingly the density of these electrons, you see, they will exhibit variations, wave-like variations on the surface, and those variations are imaged using a scanning tunneling microscope. It is a fairly sophisticated experiment, but it is not so difficult these days. And if you did that, you get these electron density undulations, which are oscillations in electron density. You see, for example, here you have no electron density, while in this region you have high electron density and so on. So those are actually due to the formation of standing waves. So in this experiment, you have a clear demonstration of the wave nature of electrons. But of course, this, as I told you, is very sophisticated experiment. You need sophisticated instruments to do the experiment, and you cannot do that in the lab. I mean, there will be some labs where it can be done, but not everywhere. Okay, so this is an example. And in this experiment, what he did was, this again is from Eigler. In this experiment, what he did was, he arranged the ion atoms in the form of a circle, and this is referred to as a circular stadium. And then standing wave patterns are set up inside this circular region, and these are the standing wave patterns. Again, clearly demonstrating the setting up of standing wave patterns within that circular region. This is, yeah, well, you see, this may be something like, how many angstroms? Maybe 30, 40 angstroms in size. Or maybe at the most 100 angstroms in size. So you have circular stadium. They also constructed an elliptical stadium where they had more ion atoms arranged in the form of an ellipse. And ellipse, as you know, has two foci, one here and the other one there. And there is the formation of, there is interference pattern within the ellipse. Why? Because you have confined the waves to an elliptical region, and they can interfere to form standing waves, and that happens. Now, what is the connection of all this with chemistry or physics or nanoscience? For that, let us think of a particle, maybe an electron. Okay. And you can say that the electron, let us say, it is confined to a very tiny box. Let us say a nano-sized box. Well, I'm sure later on in your nanoscience course, you will study how to confine electrons and so on. It is not very difficult actually. So, what you do is you imagine that you have a nano-sized box. Maybe the size is a 10 or maybe 50 angstroms. And imagine there is one electron inside. This electron is definitely a particle, so it will move, but then it will hit the boundary of the box and it will be reflected. Which means that the wave associated with the electron will also be reflected from the boundary. And therefore, these waves associated with the electron, which is confined within the box, they can form two kinds of waves. One is a time-dependent wave whose shapes goes on changing, and the other way is actually a standing wave pattern. So then how many standing wave patterns are possible? What about the simplest possible standing wave pattern? From our previous experience, we know the simplest standing wave pattern would not have any nodes. The next one would have one node, the next one would have two nodes, the next would have 3, 4, etc. Right? And because these are waves in 3 dimensions, what will happen? The nodes will be how many dimensional? 3-dimensional waves means nodes will be 2-dimensional. What is an example of 2-dimensional object? A plane. Node could be a plane, or it may be more complex objects which are 2-dimensional. So again, you may ask, what is the connection with the ordinary chemistry? And the answer is in the next slide. You think of a hydrogen atom. Okay, here is the proton, which is positively charged. Here is the electron, which is negatively charged. And the electron obviously has a wave associated with it. Remember that? Now imagine you start with the electron close to the nucleus, close to the proton. Then there is obviously attractive interaction between the two, and this attractive interaction will lower the energy of the system. And once you start with such a situation, unless you supply energy from outside, you give energy from outside, it is not possible for the electron to go too far away. So therefore, essentially what I am saying is that you cannot ionize the hydrogen atom unless you give energy from outside. So if the electron is starting close to the nucleus, and imagine it tries to move in this direction, then you see that it can perhaps go up to a certain point, and then beyond that it has to turn back and come back because it doesn't have enough energy to go to infinity. There is not enough energy to ionize the electron. So therefore, essentially, because of the attractive interaction, the electron is confined to a region surrounding the proton. So even though there is no real box surrounding the proton, what is happening is that the attractive interaction between the electron and the proton, this is the electron, that is the proton, the attractive interaction between them acts the role of a confining box. So therefore, the electron is confined to a region near the proton, which is three-dimensional. And if you confine, you see, electron is a dual thing. It has a wave nature. So therefore, if you confine a wave, this wave can have a time-dependent shape that we have seen. And it is also possible for this wave to be forming standing wave patterns. So the thing is, you see, the standing wave patterns in 3 dimensions, not in 2 dimensions, not in 1 dimension, but because the electron is moving in 3 dimensions. So for these standing wave patterns, how many of them are possible? We take our previous understanding and extrapolate that and say that, okay, there must be an infinite number of standing wave patterns. That must be possible. And the simplest one would not have any nodes. The next one would have one node. The next would have 2, 3, 4, etc. And therefore, if we think of an electron in the hydrogen atom, what are we saying? This electron can be sitting in the simplest possible standing wave pattern, which has no nodes. The next possible standing wave pattern would have one node. The next would have two nodes, and so on. Now, the students who have studied chemistry and physics, they think of what I am saying. What I am saying is that an electron within the hydrogen atom can be having different possible standing wave patterns. The simplest possible standing wave pattern has no nodes. The next one has one node. The next would have two nodes, and so on. And these standing wave patterns are actually very familiar to you people, because those are the so-called atomic orbitals. So what are atomic orbitals? The answer is that these are nothing but standing wave patterns that the electron wave forms around the nucleus. Simplest possible standing wave pattern has no nodes. That is obvious, as you would all know, because this is what is referred to as the oneness atomic orbital. The next one would have one node that could be a 2s atomic orbital or a 2px, 2py, 2pz atomic orbitals. All of them have one node each, and it is just that the shapes or the orientation of these nodes are different in space. So these are the different possible atomic orbitals. Standing waves are formed in 3 dimensions. And because you would have already studied atomic orbitals and so on, I have just drawn pictures of these atomic orbitals. Here is the oneness atomic orbital, then 2pz, then 2py will be similar. It will be, except that the two lobes will be along the y-axis and so on. You must be familiar with this. This is dz square, then dxz, f, and a more complex one, fz cube. Sorry, fx cube, and so on. We will not spend too much time on this because this would have been taught to you already, because I suppose most of you have completed the BSc degree course. Now, let me get on to other things which you would not have studied earlier. An interesting question is, do we understand quantum mechanics? I have partly indicated the answer. You look at this skier. Here is my skier, the skier, and look at the print on the snow. Of course, you see this is a mountain. These are mountains covered with snow, and you look at the marks left by the skis. These are the two skis. These are the points through which the two skis have moved. And of course, if you look at this figure and think about it, you will say that this is total nonsense. This is impossible in our world. Why is it impossible? Because you see, this person is not very big in comparison with the tree. The tree actually is bigger than him. So therefore, you see, this picture shows that one of his legs is on this side and the other leg is on the other side. How is that possible? This is impossible, and therefore this is total nonsense. Not possible in our world. With that, let us look at the two-slit experiment. Here is my two-slit experiment, okay, which we have already discussed. Imagine that you keep only slit number 1 open. Then you know that we get an intensity distribution which looks like this. Okay. And imagine I now open the second slit, then what will happen? The intensity distribution from being this one, it changes to that. We know the explanation. The explanation is that waves have passed through slit number 1 and slit number 2 and have interfered. And here you have destructive interference, here you have destructive interference, and at these points you have constructive interference. And that is what is happening. But then, I'm sorry, something has gone wrong temporarily. Okay. But then you think about this, you see, you can do this experiment with single electrons. That means you send out electrons one by one. And when you send out electrons one by one, you will always find that they will arrive at a particular location on the backstop. Maybe here or maybe there it will arrive. But when you have collected together a large number of electrons, the result is this interference pattern. That is what we have seen earlier when I showed you the video. So this is all very clear, and we think we have understood this. But now let us ask this following question, or let us think of this. See, you think of this particular point, right? And that point in the experiment where only one slit is open is this point. And the thing is, if you keep only one slit open, if only this is kept open, electrons will be arriving at that location. A finite number of electrons will arrive there. But when I have kept both the slits open, when this and that were both kept open, the experimental result is this one. And at that point, exactly at that point, none of the electrons are arriving. Not even a single electron will arrive at that location. Think about this. If you keep only one slit open, electrons will arrive at that location. But if you kept both the slits open, none of the electrons will arrive there. Well, if you wanted, you have the explanation. The waves have passed through both the slits and they interfere destructively at that location. But what is happening is that the act of opening the second slit causes none of the electrons to arrive at this location. which means that any single electron passing through the system somehow knows that I have opened the other slit also. So therefore, any electron I claim that any electron passing through the system knows that both the slits are open. And these two slits are a finite distance apart. They are not very close. Compared to the size of an electron, if you know the size of the electron, then the distance between these two slits is very large. So they are quite a distance apart as far as the electron is concerned, but still what has happened is that any single electron passing through the system knows that both the slits are open. How does it know that? How does a single electron know that both the slits are open? This is a puzzle. And the simplest answer is to say that I don't understand it. And in fact, Professor R.P. Feynman, if anybody had understood quantum mechanics, he definitely had understood quantum mechanics. And he used to go around saying that nobody understands quantum mechanics. Because he said that, you see, this is a rather difficult to understand for us human beings. The answer actually is that, strictly speaking, the answer is that the electron, when you keep both the slits open, it somehow is able to know that both the slits are open, and therefore it actually is passing through both the slits. If you keep only one slit open, then it's definitely passing through that. But if you keep both the slits open, this is the animation. You can see the animation, and that is how you have to imagine the electron actually pass through both the slits, and you cannot say it has passed through one slit. And if you ask, does it go through both the slits? The answer is it does. And then you ask, how can a particle do that? The answer is, I don't know. That is how it is. And therefore, you see, even though in our macroscopic world, this is impossible. In the microscopic world, this is exactly what the electron does. If you have two slits, it passes through both the slits. And that is what makes quantum mechanics is very strange. And you can actually there are more interesting things happening here. I don't have the time. But if you suppose you do an experiment trying to determine whether it has passed through one slit or the other, then you will find that whenever you do an experiment, it is passing through only one slit. But if you keep both the slits open and if you do not try to determine whether it has passed through one slit, then you will find that there is interference pattern, which implies that it has passed through both the slits. So if you observe it, it is passing through only one slit. And if you do not, it passes through both. So the next question is, how does an electron propagate? How do you describe the propagation of an electron? Or not just electron, you can think of any quantum mechanical particle, protons, neutrons, helium atoms, and so on. How do they propagate in space? Answer is straight away given here by the professor through all possible paths. And that, of course, sounds like nonsense. And I will explain why he says that the electron moves through all possible paths. So for that, you have to think of a more complex experiment, a more complex version of the two-slit experiment. Here you see earlier we had only one wall, and that one wall had two slits. But now I say that I have 1, 2, 3 walls. Each one of them has two slits. So therefore, the experimental arrangement is more complex. You have a source of electrons at this point, and you have two slits here, two slits there, two slits there, and then here is where I detect the electron. So the experiment consists of measuring the intensity or the number of electrons arriving at different locations on the backstop. So if you keep this arrangement, then you will see that the electron could have taken this path, the green path, that green path. Oh, it is a blue one. I mean, on my screen, it appeared to be green. Let me correct that. So it could have taken this blue path, or it could have taken this brown path, or it could have taken this rather dark brown path, and so on, or red path. So these are three different possibilities. And what will happen, you see, if you wanted to calculate the intensity of the electron beam at this location, what you will have to do is you will have to take contributions from these different possible ways in which the waves could start from here and end there. There are what I have drawn here are actually three different possible ways, but if you think about this, you see there are 8 different possible ways in which the waves could start here and end up there. Because you see here you have 2 slits on the first wall, then you have 2 slits on the second wall, so 2 into 2, 4 possibilities into 2 coming from the third wall, and therefore there are 8 different possible ways in which the waves could start here and end there. And so therefore to the wave function I would expect 8 different contributions, I1 plus I2 plus etc. until psi8, and you add them up, you will get the total wave function. And once you get the total wave function, you take its magnitude and square it. That will enable you to calculate the intensity at this point. So that is the prescription that we have already seen. So if you agree with that, what we will do is we will make the experiment more complex. So what is the complexity that I will introduce? Well, here what I have done is I have said that there are, I think, I don't remember the number, but maybe 12 volts between the source and the detector. The source is here, the detector is there. And each one of these valves have 4 slits. So through the first valve, you have the possibility, 4 possibilities. Through the second one, you have 4 possibilities. Therefore, in total, you have 4 to the power of 12 possible ways in which the electron could travel. And that you will realize is a huge number. Okay, and then if you wanted to calculate the wave function, you have to calculate the contribution from each possibility, add them up, contribution to the wave function from each possibility, add them up, and you will get the total wave function. And once you get the total wave function, take its magnitude and square it. You will get the intensity. Okay. Easily you can make this more complex. How? I will double the number of slits. Okay, that seems to have not happened. Let me see whether I can reproduce it. Sorry. Okay, yeah, well, you see somehow that particular slide seems to be missing. You can imagine, let me just go back once more. Okay, yeah, well, the thing that you should imagine is this. Make more slits. I hope you can see. I'm making more slits on the first wall. Similarly, you can make more slits on the second wall and so on. So therefore, that is easily possible. You make more slits. And then what would have happened? You see, the number of passes that you have to consider have increased. So similarly, what I'm going to do is I'm going to increase the number of slits. I make more and more slits. What will happen? The number of passes that I have to add will go on increasing, and eventually, imagine I have reached a situation where I have made so many slits that the walls have disappeared. Therefore, you see, the walls are there in my mind, and I have made so many slits in my mind in these walls so that each wall has disappeared. So therefore, what am I talking about? The walls are really not there, and therefore I am talking about the propagation of the electrons in free space. But then, how do they propagate? Well, you see, when there were these walls, you had to think of paths. And when you increase the number of slits, what is happening? The number of paths is going on increasing. So eventually, when you are in the limit where the slits are so many that the walls have disappeared, the number of paths has increased to a very large extent. So therefore, what is happening is that if you are thinking about the propagation of the electron in the free space, this is how you have to do. You have to think of the electron is starting here, and you want to calculate the probability of finding the electron at that location after some time. Right? I want to calculate the probability of finding the electron at this location, given that it has started here now, and I want to calculate the probability of finding it at this particular location after 10 nanoseconds, let us say. Then the picture that I have shown you implies that I have to think of all possible paths that the electron could have taken. Maybe the green path is a possibility, this red path is another possibility, this blue path is another possibility. You think of all the different possible paths that the electron could have taken. But they have to satisfy two conditions. They all have to start here now and end there after 10 nanoseconds. You think of all possible paths, you say I can easily draw another path. But the only condition is that it has to start here and end there. And the electron has to be moving such that it traverses this path within 10 nanoseconds. So all those paths you take, each path makes a contribution to the wave function. So therefore, you calculate the contribution to the wave function, then add up all the contributions from the different possible paths, and that will give you the total wave function. And once you get the total wave function, take its magnitude and square it, you will get the probability density of finding the electron at that location. So this is how the things are in actuality. So therefore, the conclusion is that all possible paths contribute to the wave function. Now, what is the contribution of a given path is the next interesting question. I will not spend too much time on this. See, for example, you are given this particular path. What is the contribution to the wave function from that path? Well, if you think of this particular path, what is the meaning of this path? You see, if the electron followed this particular path at each instant of time, it has a position. That means you know the position of the electron. Let me denote it by x of t. You know the position at each instant of time, and if you know the position, you can differentiate that and calculate velocity also. So at each instant, you definitely know the position of the electron, you definitely know the velocity of the electron if it followed that particular path. But in actuality, the electron follows all possible paths, and that is why position and momentum are not so certain. But if it were following this particular path, it will have a position at each instant of time. So if you know the position at each instant of time, you can position and velocity at each instant of time, you can calculate the kinetic energy at that instant of the particle. You can also calculate the potential energy of the particle at that particular instant, take the difference between the two, and then you can integrate from the initial time to the final time. This is an object very familiar to physicists, which is referred to as action. In classical mechanics itself, this quantity is known. So what is it? You take the difference, not the sum, between kinetic and potential energies, multiply it by dt, the time interval, and integrate it from initial time to the final time. You get action. And what you have to do is, if you want to know the contribution of this particular path, you first calculate the action for that path. Action is given by this expression. You calculate the action, multiply it by I, divide it by h cross, take its exponential. And then you sum over all, you do that for all possible paths, and then you sum over the contributions from different possible paths. So therefore, you have a sum over all possible paths. And then you see you have to multiply it by a suitable constant, wave functions have to be acceptable and so on. You will study that later on, I'm sure. So this is essentially a normalization factor, so-called normalization. So this is how you get the wave function in this kind of approach. Yeah, the expression that I had used is already written here. So action is nothing but difference between kinetic energy and potential energy integrated between the initial and final times. So that is action. You take that action, put it there, and that is the contribution of a given path. Well, we will not worry about this. Here is an animation. A very nice animation. So you see what is done is, I think of the two-slit experiment. First we do the experiment with particles, and that is what you are seeing. Okay, here you are doing the experiment with particles. Then the same experiment will be done with waves. And then you will see the same experiment done with a quantum object like an electron. So that is what you are going to see. So let us proceed. Now it is going to be done with waves and see what happens. Obviously, what has happened is that you get interference pattern. And imagine now that the experiment is done with, sorry. The experiment is done with electrons, a quantum object. This is, yeah. See, with a quantum object, you see what is happening. You have the electron coming out from the screen, sorry, from the source. And when it moves, you see it is moving as a wave. You can see that there is a wave that is moving. And that wave actually passes through both the slits. And then you will see that the wave hits the detector somewhere here. But then when you detect, you see the wave has suddenly turned into a particle. When you detect, it is a particle. So let us see that. So you see it is detected, and when you detect, you see there was a wave that was spread out, but that has actually collapsed and it is now just a particle. And when you have done it with sufficient number of electrons, you see that there is this interference pattern. So that is how it is. This is a very nice animation. I think somewhere at the end you should see. Okay, this is the place where it is available. If you search in the web, you should be able to find it. Okay, this we have seen already. How am I doing with the time? How much time do I have left? Is it okay if I spoke for another 10 minutes?
Yes, sir. You can continue.
Okay. I want to give you a nice analogy. I told you there is this Captain Kudil. Here he is. He likes to drink. And let us see. See, imagine that this person, I say this is a, well, actually, it says Haddock in the evening. That should have been corrected. This is actually Kudil in the evening instead of Haddock. Anyway, it doesn't matter. This is the person who is going to get drunk. Every evening he goes to the bar or to the local toddy shop and gets drunk. So he's there, let us say, up to 10 o'clock in the night. And 10 p.m. he comes out of the bar. And he's completely drunk, so he has no sense of direction. So he executes what the mathematician will refer to as a random walk. What is a random walk? According to a mathematician, it is a walk in which he takes one step in one direction, and the next step that he takes is in a direction that is independent of the direction of the previous step. So if he takes a step in this direction, the next step could be in any direction. Maybe it is like that, or maybe it is like that, or maybe it is like that. That is the kind of walk that he executes. And this is a drunken person's walk. And so suppose I observe this guy, let us say for an year, starting from January 1st until December 31st, I observe him. On the first day, he will come out and he will follow a path, which may be something like this. But on the second day, would he follow this path? Definitely not. He may follow a totally different path, or maybe he may follow that. So if I keep on observing, you see each day, the path that he takes is different. And this is what you refer to as a random walk. So suppose I have observed him for 365 days. The next day, that means the next year, January 1st, if you ask me, where will Mr. Kudiyal be after 1 hour? Will I be able to answer that question with any certainness? I shall not be able to answer that question with definiteness, but I can say, okay, there is a fairly large probability that he may be found within 1 kilometer of the bar, but very little probability that he will be found 5 kilometers away. So therefore, if you ask such a question for a random walk, then you can make only probabilistic predictions. Notice that this is very similar to the case of the electron. If you start an electron at this location, this now, you cannot say where it will be after some time. You can only talk of the probability of finding the electron, let us say at this location after some time. And how do you calculate the probability? The answer is that you have to think of all possible paths that the electron could have taken. Each path makes a contribution to the wave function. Notice that it makes a contribution to the wave function. So you have to evaluate that contribution to the wave function, then sum up all the contributions from the different possible paths. And you will get the total wave function, and you take the square of that, you will get the probability density. So that is the prescription. Now let us see, what about Mr. Kudiyal? Well, the answer is the following. You say you can only talk of probability density of finding him maybe at this location. I mean, let me make the question more concrete. I know that he is going to start here at 10 p.m. And what is the probability of finding him inside this region at 11 p.m.? The answer is, you see, you have to think of all possible paths that he could have taken. One possibility is this path, but this path will not end up at that location at 11 p.m. So therefore, you have to think of another path, maybe something like that, starting there and ending here at 11 p.m. or another one like that, which is something like this, starting at the original point and ending here at 11 p.m. and so on. So you have to think of all these possible paths. And you can say that, okay, some of these paths are less probable than the other because you see they are very convoluted. You see, for example, a path like this may be very improbable in comparison with a path like that. So therefore, it is possible for it to assign a probability to each possible path. So therefore, here the prescription is that you think of all possible paths that are allowed. Then each path makes a contribution to the wave, to the probability. Now, in the earlier case, in the case of the electron, it was a contribution to the wave function, but in this case, it is a contribution to the probability. So the idea is that some paths are more probable than others. So therefore, for example, you start here at 10 p.m. and want to calculate the probability density of finding him at this location at 11 p.m. Then you have to think of all these paths which start here and end there at 11 p.m. All paths are possible, but some of them are more probable than others. So therefore, you have to calculate the contribution from each path and then make the sum. So therefore, essentially the probability of finding the drunken walker at this location after some time is a sum over all possible paths. So each path makes a contribution to the probability. Well, the difference between quantum mechanics and this is that in this case, the path is making a contribution to the probability directly, whereas in the previous case, you see the path is making a contribution to the wave function, and you have to calculate the contribution from each path to the wave function, after which you add up all these contributions, and then when you add up these contributions to the wave function, the paths may interfere or constructively or destructively, and therefore the final wave function's answer may be 0 or negative and so on. Whereas in this case, the contribution is to the probability, and that contribution is always positive, and therefore it is not possible for the contribution from one path to be cancelled by the contribution from another path. That is the major difference between the behavior of the electron and the behavior of a drunken walker. Otherwise, speaking mathematically, they are very, very similar. And this particular approach to quantum mechanics is what was referred to when I was introduced, that is known as the path integral approach. An approach which is very nice and beautiful, one of my favorite approaches to quantum mechanics. In fact, I make use of this approach in all my research, most of my research. And maybe in the references, I'll give you a reference to the approach. But it is fairly sophisticated when it comes to the mathematics. And so unless you are mathematically inclined, you would find it difficult to read. Now, let me leave you with some references. There is a very nice book written by George Gamow. I remember Calicut University Library had this book when I was a student, when I was a faculty member there, I think. It must still have it. The book is written by George Gamow, called Tompkins in paperback. This is actually like fiction. The hero of this is actually a series of articles that was published in some newspaper by Gamow. The hero of the story is Mr. Tompkins, who is a clerk in a government office, and he has no interest in physics. But his girlfriend is the daughter of a physics professor at the university, and so when the professor gives lectures on physics, which are meant for popular man, he feels obliged to go and sit there and listen just to please his girlfriend. So he goes there and sits, and the professor talks about quantum mechanics. He talks about relativity, chemical reactions involving sodium and chlorine, and so on. And see, he has no interest in science, and so what happens is that he has to listen to something, but he is completely disinterested, so he falls asleep during the lecture. And when he falls asleep, he starts dreaming. And he dreams about quantum mechanics and combination of sodium and chlorine atoms and so on. Now, in our world, you know that the value of H cross is very, very small. It is of the order of 10 to the power of minus 34 in SI units. So H cross is very small, so therefore the effects of uncertainty principle cannot be seen with our eyes. But what Tompkins dreams is a world where the value of H cross is 1 unit, 1 in SI units. That means it is 10 to the power of 34 times larger than the actual H cross. And in such a situation, the wave nature of particles you can see. For example, Tompkins has a car. He puts the car into the car shed, closes the door and locks it, and goes to sleep in his flat. And the following morning, when he comes out of his flat, he finds that the car has behaved as if it is a wave, and the wave has actually passed through the closed door, leaving the door intact. So that is a phenomenon that waves can do. They can pass through barriers while particles cannot. So the car, which has a wave nature, it exhibits the wave nature and passes through the door, which is a barrier. And so he finds that the car has come outside, leaving the door intact. There are other similar things that you will find very interesting in this book. So very strongly recommended for you to read. Another book, a nice book, is Alice in Quantum Land. You know the classical story where Alice goes to the Wonderland. But in this story, Alice, instead of going to the Quantum Land, instead of going to the Wonderland, she goes to the Quantum Land, and she is able to see quantum phenomena with her eyes. So a very nice book. There was an Indian paperback edition available. I don't think it is available now. Maybe if you look into your libraries, you may find it. There is another book called Schrodinger's Cat, written by Gribin. There is a very famous paradox called Schrodinger's cat paradox. I have not touched upon the details of this at all, but it is very interesting. What Gribin does is he gives an introduction to the cat paradox, and at the same time he gives an introduction, very nice introduction to quantum mechanics, which is not mathematical. So this is another strongly recommended book. Then there is another book, Cropper. This again, I think, is available in the university library there. It is called Quantum Physicists, written by Cropper. This gives you biographies of all the people who were involved in the development of quantum mechanics, but at the same time, it gives you an introduction to the quantum mechanics itself. Well, Gribin had written Schrodinger's cat. If you have cat, then naturally you will have kittens. So he has written another book called Schrodinger's Kittens. Since the quantum mechanics was formulated, people have been trying to find a situation where it doesn't work. And this book actually summarizes all the details of all the experiments which have been done until 1995. And fortunately for us, you see, quantum mechanics has withstood the test. In no experiment, quantum mechanics has ever been violated. Now, the book by Gamow is old, and therefore there is a newer version of it called The New World of Tompkins. And that is the book. There is another very nice book called the Quantum Electrodynamics, QED. This is by Feynman, an authority, or a person who was an authority. Very nice book, non-mathematical. And this is the book that I was referring to. This book gives you an introduction to path integrals, my own favorite approach to quantum mechanics. If you are mathematically inclined, then this is strongly recommended. Okay, what else do I have? Okay, well, this is a website that was available, but I don't think it is available anymore. So I shall leave you with this question. What do you think of quantum mechanics? I hope I have persuaded you that this is not the way you should be thinking of quantum mechanics, but it has to be something more beautiful than this lady. Let me see whether I have anything more. Okay, I would like to thank you all for your attention, but I just want to add one more thing. There are lectures of mine available on YouTube on quantum chemistry. All that you need to do is you can search my name or quantum chemistry, and you should be able to find them. They were recorded by the NPTEL. Some 49 videos are available. If you find the lectures interesting, you can have a look at them. But of course, you see, listening to YouTube lectures can be boring. So you have to withstand that boredom. And then you can listen to the lectures. So I would like to thank the organizers for giving me this opportunity. It has always been a great pleasure for me to speak about quantum mechanics. And I hope the participants have found it interesting enough that they will be persuaded to study it further. And of course, the only pity is that I have not touched upon much of details of nanoscience. But essentially, the ideas that I have outlined to you are all of great importance in nano technology and nanoscience, because essentially what you are doing is you are confining electrons usually to nano-sized regions, and then their motion has to be described using quantum mechanics. For example, the path integral approach that I have spoken about. The more traditional approach to quantum mechanics is not in terms of path integrals, but it makes use of what is known as the Schrodinger wave equation. And the Schrodinger equation is usually introduced as a set of postulates. And the next speaker, Professor Kannan, will actually do that, I believe. So you see, the path integral approach that I have spoken about is very nice, but it is very difficult to use in actual calculations. And therefore, what is done is you introduce quantum mechanics as a set of postulates. And that, I believe, is what Professor Kannan will do. And I am sure you will enjoy the postulates and the remaining things that will follow by other speakers. And wishing you all good luck in your future endeavors. Let me conclude and thank the organizers once again. Thank you.